Hey guys, welcome to section 2.6, looking at kinetic friction. So we'll have one more static friction after this, and then we'll start reviewing and getting ready for our test next week. But first, kinetic friction is, first off, we kind of have an understanding what friction is. It is the force that opposes motion. And the word kinetic simply means the thing is moving. So as we look at this, friction is, yes, a resistive force. There are many types of there are different types of forces that occur in nature, but we use friction all the time. Friction is the whole reason we can walk forward. We talked about Newton's third law. If I push on something, I have to have an equal and opposite reaction. Well, if there's no friction between my foot and the floor, I can't move forward. There's no other opposing force there. And so my example here is, what does friction have to do with sandpaper? Well, we all kind of know what sandpaper is. It's a very rough surface, and it doesn't slide well. It actually takes chunks of the wood off if you're using sandpaper. And so I just want you to envision what the sandpaper looks like, what it feels like. It doesn't slide easily. Friction is the reason objects stop rolling or sliding along a surface. It's the reason it is difficult to start pushing a heavy box along the floor. So there's a couple of different types of friction. We have the friction we're going to be using between like a box and the floor or something like that. Air resistance is the friction between solid objects and air, and so sometimes we neglect air resistance, and there's a reason for that. And friction between two fluids is called viscosity. And so when we think of viscosity, I want you to think of like regular water. It has a kind of a low viscosity. And if you think of honey or oil, it has a higher viscosity than water. So it's thick. It doesn't flow very well. So that's what viscosity is. But basically, the type of friction we're using, we're going to be using air resistance and the friction along objects being pushed. And so the question is, where does it come from? Well, when you zoom in between these two surfaces, and I have this blue surface and this pink surface here, what we're actually looking at are these microscopic little imperfections of valleys and mountains, and they interact with each other and they lock up on each other. The smoother an object is, the less of those imperfections you have, and which means it's easier to flow across. If you think of sandpaper, it's going to have lots of little ridges and mountains that grab onto things, and that's what makes the sandpaper feel so rough. But we use just the box sliding on the floor. We don't really zoom in this class. It kind of goes beyond the scope of what we're looking at. But when we go down in the middle of it, we see all of those different interactions at the microscopic level. That's pretty much what we think of. So friction force, we have to have a way to express it mathematically. Friction that acts on an object that is already in motion is called kinetic friction. So that's the first piece we're going to be looking at. Something already sliding. We write Fr equals mu. So this guy right here is called mu. That funny looking U, mu sub k, that means the coefficient of kinetic friction. And then we have our Fn, our normal force. We got good at figuring out what he is. And then once again, my friction force, my FFR. Once again, mu sub k is called the coefficient of kinetic friction, and it is different for every pair of surfaces. And the normal force is Fn. On flat surfaces that we'll be dealing with, it's simply equal to the weight of the object. And so I want to talk a little bit about what the coefficient of friction is. Here we have a table that has all of these coefficients of kinetic friction. So wood on wood is 0.2. That seems to make sense. Ice on ice, so pieces of ice sliding against each other, is 0.03. So very low. Metal on metal lubricated, so think insides of engines. Steel on steel unlubricated, so think about the train systems. Like when a train's sitting on railroad tracks, it's just basically steel on steel. Rubber on concrete is very important for us. That's how we drive around. And rubber on wet concrete, we have less friction that is available to us. So that's why we have to be careful on when it's wet outside, when it rains. One thing that's kind of cool is if we look down here, we have this human joints in limbs. Sometimes you hear the term synovial fluid. All of the fluid in our joints has a very, very low coefficient of friction, which means it's really easy to move our joints. And that's important. We like to be able to move our joints. So when we analyze our problems here, we use the same principles we've been using all along. So here we have a person is accelerating a crate along a rough surface. So if we're taking notes, here's a good thing to write some things down. First, we draw the crate's free body diagram. So here's my block, my crate. Pause it if you need to. And then I have FG pointing down. FG is equal to mg always. So I wrote that out there. Then I have my normal force. That's always going to be pointing up. The applied force, that could be the push or a rope, something. I just know that that's the force being applied to the object. And then I have my friction force. It's going to be pointing away from the applied force. And then I have my acceleration arrow, which means I kind of know which way the motion is. So that's which way it's accelerating. Then we determine net force in the x-axis. So net force sigma fx equals max. Those subscripts simply mean in the x direction. And then the applied force minus friction force equals ma. That's where we've been so far. Remember, if it's not accelerating, these two guys get to be equal to each other. In this case, I know that the applied force has to be bigger than the friction force, which results in my acceleration here. There's an imbalance there. Determine what's going on in the y direction. Well, net force in the y direction. I know it's not accelerating in the y direction. My Fn, my normal force, my mg, my weight, and then I know they're equal. And then what happens is our problems end up saying all of this stuff plugged in, and I'm going to be looking for applied force, mu, mg, a variety of things. It just kind of depends on what I'm looking for, what's given to me. So, that being said, let's take a look at our first example. The coefficient of kinetic friction between an object and the horizontal surface upon which it is sliding is 0.4, and the mass of the object is 3.2 kilograms. What is the force of friction? So, here's my free body diagram, Fg, mg, Fn, applied force, and friction force. And I know it's going that way. I have direction of motion, acceleration. So we need those arrows to make sure we know which way friction is pointing. So my given of my mass of 3.2 and my mu sub k of 0.4, that's how I'd write that. And then of course I know gravity is 9.8. My friction force defined. So this is one of the equations you get on your formula sheet. This is what you have right here. And so the normal force is always equal to the object's weight. Combine the two formulas. So the force of friction is just mu times the normal force, or mg. And then we plug everything in. So in this case, an object that is sliding, and as it's going along, has 12.5 newtons of friction force acting on it. So there you go. Here we have a slightly different question. It's asking me to find the coefficient of friction, and then I know both the mass of the mass of the block, 10 kilograms. The applied force is 60, and then I know the acceleration rate on this one. So it's a little more detailed than the last question was. Here's my free body diagram, mg, Fn, applied force, and friction force. Notice on this one, we tried to draw this that says the applied force is greater than the friction force. The arrows help us to see that. And then the red acceleration arrow pointing to the right. So given, there's my mass, my applied force, my acceleration, vertical direction, Fn equals mg. Friction force equals mu times normal force, which is mu mg. In the horizontal, I know the applied force minus the friction force is mass times acceleration. And then I substitute my mu mg in for my friction force. I then have to solve for mu. So once again, slow this down a little bit if you need to. I have mu equals the applied force minus ma over mg, just a little bit of algebra. Substitute the values in, and then I should get 0.6 for the coefficient of friction between the floor and the crate. So at this point, those are the two basic questions you're going to have. Find mu, find a... there's a couple that you might have to find the mass of the object. So it's not too bad. So for your assignment, please do the classwork. Once again, those are great questions to make sure we understand what's going on at the basic level. I will be checking those to make sure those are done. And then your problem set is due via MyTrinity. And then we will have a short mini quiz. I'll make sure we have a couple of things nailed down before we do that on, Thursday for you guys. So make sure you are ready. All right. Thanks for watching. See you guys later. Bye.